Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I am going to be talking to you about the Fourier series, where the Fourier series is a mathematical concept introduced by Jean-Baptiste Joseph Fourier, where he proposed that any periodic function, no matter how complicated, can be reconstructed as a sum of simple sines and cosines, or equivalently, complex exponentials, as shown here. And in this video, we'll be talking about the recreation of periodic functions using the complex exponential. And in this situation, it's going to be multiplied by this coefficient ck. And in another video, I'm going to talk about how we transform this complex exponential to sine and cosine waves. Before we dive into solving equations, we want to talk about a situation where the Fourier series can be used to kind of give it intro to why it is useful and why we need it and where we use it at. So imagine a situation where you have a light bulb. You have a switch that's connected to a light bulb emitting light. And this light bulb, there is a light sensor in the room that is collecting a signal, which is periodic. Imagine you're switching the light on and off at a periodically. Okay. And what you want to do actually is you want to transmit this signal, this square wave in this situation, which again has a fundamental frequency because it's periodic. And you want to transmit this through a transmission line. And what you're going to notice is that it's going to pick up a lot of noise. So the signal might actually look something like this. Okay. So what we essentially want to do is we know that this signal has a fundamental frequency, omega naught, but the noise signals are not harmonics of this omega naught or fundamental angular frequency. And since we know that they're not part of the harmonics of the fundamental angular frequency, if we find those frequencies that the noise are resonating in, we can eliminate them using filters like RC, RL, RLC filters. So essentially, when we do the Fourier series, we're going to find this omega naught for the sine wave and its different angular as different harmonics, k omega naught. And then we're going to use filters like low pass filters, band pass filters, band stop filters to filter out the frequencies at which the noise is coming in, right? Or you could say let only the fundamental angular frequency pass through and get rid of all the other frequencies. That's what I mean by filter out. And as a result, when you filter those frequencies out, you're going to get back your nice looking sine wave. Oh, sorry, your nice looking square wave as a function of sines and cosines, or this complex exponential added up together. And what's going to happen is you can go ahead and connect this to maybe like a speaker, and you're going to get a nice signal. Right. I hope this concept of me drawing this out makes sense. If it doesn't, please let me know your concerns down in the comment section below, and I'll be sure to get to you. So what does Fourier actually say in terms of mathematically? He says, all right, give me a periodic function. So let's take this function here, this simple square wave minus t over 2, t over 2 to t, where this is x of t. So x of t, we could say, let's say that this is a and this is minus a. X of t is going to be a to minus a from 0 t to t over 2, t over 2 to t, right, to t, right? So I'm basically talking about from here to here and from here to here. He says that I can reconstruct this signal right here using the following. I could say that x of t is equals to, and I'm going to write out the entire thing, the sum of k is equals to minus infinity to infinity. This ck, but what this ck actually is 1 over the fundamental period integrated by 1 period x of t e to the minus jk omega naught t dt, and then multiplying all this by e to the jk omega naught t. Okay, where this here is what we consider ck, or we also consider that the Fourier series coefficient sequence, where in this example x of t here is simply going to be a for a period 0 to t over 2 and minus a for a period t over 2 to t. Now, to be completely formal with it, I'm going to talk about the Fourier series analysis theorem that says that the Fourier series coefficient sequence ck of a periodic function x with a fundamental period t is given by, again, this guy right here, which is going to be ck is equals to 1 over t integrated over the period x of t e to the minus j k omega naught t dt. Let's keep in mind that the fundamental period as well, t, is simply equals to 2 pi over omega naught. So that means that the fundamental angular frequency omega naught is equals to 2 pi over t. Now, given this theorem, right, the Fourier series analysis theorem, we need to prove this, right? Why can we say that the coefficient sequence ck is equals to this integral, right? Why can we say that? And proving this is relatively simple, right? It tells you that given a periodic function x, so my periodic function in any case, right? For example, in this case might be, right, x of t, which is that square wave that I drew up here, right? So given a periodic function x of t, Fourier says, okay, I'm going to sum up from k is equals to negative infinity to infinity. I'm going to multiply by this ck, or this coefficient sequence, and then I'm going to multiply by this complex exponential e to the j k omega naught t, where again omega naught is that fundamental frequency and k it's all of its harmonics. So let me just recap again. This here is given to me. It's that square wave. I hope that makes sense. K is just, right, whole numbers, right? 1, 2, 3, 4, all the way to infinity. And omega naught is the It's basically 2 pi over t, which is also given to me, right? So if I'm given this t here, right, omega naught is simply 2 pi over t. So I hope that makes sense. So everything is given to me except for this ck. And that's what I need to solve for. And I need to prove that it's equated to this. Okay? So to begin, what I'm going to do is I'm going to multiply both sides by e to the negative jn omega naught t. I'm going to multiply this side as well by e to the negative jn omega naught t. Then I'm going to take the integral on both sides, on both periods. So integrated by period t, x of t, e to the negative jn omega naught t is simply equated to the integral of the sum, well, the integral from 0 to t, or the period t. K is equals to negative infinity to infinity. Ck e to the j. I can do k minus n here. Omega naught t times dt. And there's a dt here as well. Okay. And what I'm going to notice here is that, okay, this here is a constant. So it's not dependent on t. So essentially, I can pull this out. So this is a constant. And essentially, this here is my integral. All right. And what I'm going to say is that the integral of 0 to t e to the j k minus n omega naught t dt. Again, there's a summation here. That's fine. To infinity. I'm going to say that this is equals to t when k is equals to n and 0 otherwise. So now let's go ahead and prove this. Okay. So in order to do this, we need to consider two cases. A case where k is equals to n, right? And in a case where k is equals to n, this summation goes away because k is a singular value, right? We're not taking a sweep. Okay. So this goes from 0 to t e to the j. It's going to be 0 omega naught t, simply because when k is equals to n, k minus n is 0. Dt, so this is equals to the integral from 0 to t times 1 dt, which is simply equals to t integrated from 0 to t, which is equals to t minus 0, which is simply just t. So this is this value. Now keep in mind, again, this is very important. In this case, the summation disappears. All right. Now the second case, case number 2, is a bit more complex. This is k not equals to n. All right. And when k is not equals to n, let me go ahead and say that m is equals to k minus n. Okay. So as a result of this, I get the integral from 0 to t e to the jm omega naught t dt. When you take the integral of an exponential, it just becomes e to the jm omega naught t over jm omega naught over the constant being multiplied by the variable t. So evaluate that from 0 to t. All right. And essentially, as you can see, only the numerator has a variable t. So I'm going to say then that this is simply equals to e to the jm omega naught times t minus e to the 0, right? Because again, it's being evaluated at 0, divided by jm omega naught. All right. So this is where it becomes a bit tricky. So keep in mind that omega naught we said was 2 pi over t. So these t's cancel out. And what is e to the jm times 2? We need to look back at our unit circle and notice that e to the jm times 2 pi is always going to be at 1, simply because when m is any whole number, so 1, 2, 3, 4, this is always going to be at 1. As a result of that, we get that this here is 1. Obviously, e to the 0 is 1. So this is 1 minus 1 over jm omega naught, which is simply equated to 0. And that is this case here. All right. So since every case that k is not equals to n gives us a 0, we're only going to take the case where k is equals to n. So then essentially we say that this is equals to ck times t, where k is equals to n. Again, remember, this summation goes away because k is just one value. It's just a single value for ck. So let me go ahead and start this and rewrite it down here just to clarify the work. All right, we can say then that t times ck is simply equals to the integral of t x of t e to the minus jn omega naught t dt. Again, this n here can also be considered k. So I'm going to go ahead and just change it up just to k. And essentially when you solve for ck, you get 1 over t integral of t x of t e to the minus jk omega naught t dt. And that ends our proof, right? Okay. And this is a very, very powerful tool, very, very powerful proof. If you have any questions about this, if this wasn't clear, please let me know down in the comment section below, and I'll be sure to get to you. And again, what I can do is I could take it full circle and say that I can reconstruct any periodic signal by saying that the reconstruction, x of t, is simply equals to a summation as k is equals to negative infinity to infinity times this c of ck, which is basically 1 over the fundamental period integrated around the fundamental period from 0 to t, x of t, which again in our case is that square wave, right, times e to the minus jk omega naught t dt times e to the jk omega naught t. So again, this case here is going to be our ck, right? If you found the video helpful, please give it a thumbs up. If you have any questions, please leave them down in the comment section below. The next video I will do is showing this in terms of sines and cosines. And I'll try to do the example for the sine wave. So look out for that. Please subscribe to my YouTube channel. It really helps the algorithm. And share my YouTube page. Thank you.